this particular video, we're going to see how we can encode the tridiagonal matrix algorithm in MATLAB. Before that, let us have a quick look into the algorithm itself. So assume we have equations of the form AI Ti is equal to Bi Ti plus 1 plus Ci Ti minus 1 plus Di. It's a set of equations where I can run from 1 to n. Of course, the unknowns in this problem are the nodes T1, T2, T3 all the way up to Tn minus 1 and Tn. Now it is apparent from the equation that if you put I is equal to 1, then you will end up with a term T0, and T0 is by definition 0 because it does not exist, and as a corollary C1 is also equal to 0 because we don't want T0 to exist. So if I put I equal to 1, this particular term has to be 0. Similarly, when I is equal to n, Tn plus 1 will appear over here, and even that term has to be 0, and therefore Bn has to be equal to 0. So the structure of this equation, if I write it down in the form of a matrix, will look something like A1, B1, 0, 0, 0, 0, 0. Rather, this should be minus B1. So over here we have minus C2, A2, B2, 0, 0, 0, 0, 0, minus C3, A3, B3, 0, 0, 0, all the way up to Cn minus Cn. This should be minus, and this An. So all of these should be 0. So T1, T2, all the way up to Tn is equal to D1, D2, all the way up to Dn. So this is the matrix form of the above tridiagonal system. So the crux of the problem of the tridiagonal matrix algorithm is that we must cast the tri-banded equation, the tridiagonal equation, in the form of this particular matrix. Rather, let me not put alphabets over here. I'll just denote the non-zero components of the matrix by dots. So we observe that in the last row there is only one dot. So essentially what we will do is forward elimination and thus remove these particular coefficients, all the C's, and in doing the row and column operations we will end up with the last row which only has the diagonal element. And if it has only the diagonal element, we directly obtain a solution for Tn. We directly obtain a solution for Tn. Now, if Tn is known, in this particular set of equations, Tn minus 1 and Tn are unknown, but we just found out Tn from the previous equation, and this equation would help us in solving for Tn minus 1. So this step in which we use Ti to solve for Ti minus 1 is called as back substitution. So this algorithm consists of forward elimination in which the tridiagonal matrix is cast in the form of a two diagonal matrix where the last row only has the diagonal element, and the next step is backward substitution. So as the name suggests, backward substitution will obtain the value of Ti by using Ti plus 1. In this case, it will solve for this particular element because this particular element is known from the previous step. So without further ado, let me go straight to the algorithm. So we have Ai Ti is equal to Bi plus 1 Ti plus 1 plus C should be Bi Ti plus 1 plus Ci Ti minus 1 plus Di. However, we just discussed that the forward elimination should cast the equation in the form Ti is equal to Pi Ti plus 1 plus Qi. Essentially, it is saying that the backward substitution implies that the value of Ti will be found out by some linear combination of T at the next level, that is Ti plus 1. Okay. So if I call this equation 1 and equation 2, from equation 2 I can directly write Ti minus 1 equal to Pi minus 1 Ti plus Qi minus 1. I will call this equation 3. Now we can eliminate Ti plus 1 in equation 1 with the help of Ti minus 1 that we have in equation 3. So using 3 in 1, we obtain Ai Ti is equal to Bi Ti plus 1 plus Ci Pi minus 1 Ti plus Qi minus 1 plus Di. Let me combine the Ti term appearing over here and keep the Ti plus 1 over here. So I obtain Ti Ai minus Ci Pi minus 1 is equal to Bi Ti plus 1, which is this term, plus Ci Qi minus 1 plus Di. And then in the end I obtain Ti is equal to Bi by Ai minus Ci Pi minus 1 Ti plus 1 plus Ci Qi minus 1 plus Di by Ai minus Ci Pi minus 1. And thus a keen observer will note that if a comparison of this particular equation with equation 2, this particular equation, if I call it as equation 4, if I compare 2 and 4, this particular coefficient is the same as Pi and Qi is equal to this particular coefficient. So Pi is equal to Bi by Ai minus Ci Pi minus 1 and Qi is equal to Di plus Ci Qi minus 1 divided by Ai minus Ci Pi minus 1. So this gives us a recurrence relationship in the sense that Pi depends on Pi minus 1 and Qi depends on Qi minus 1 and Pi minus 1. So it's sort of a recurrence relationship. It's like a telescoping of P once the next step is, once the ith step is known, Okay, once the ith step is, or rather once the I minus 1th step is known, the I step will be known. It is interesting to note that because C1 is 0 and Bn is 0, okay, then P1 will become B1 by A1 and Q1 will become D1 by A1. Okay, we just set I equal to 1 in this recurrence relationship, and obviously this you can easily find out by just writing the first equation for the very first node, that is, we disregard C1. In this particular equation, once P1 is known, so if I put I equal to 2 over here, I will have a relationship between P2 and P1 and Q2 and Q1 and P1. Since we have Q1 and P1 already known in this equation, we can now find out P2, Q2. Once P2, Q2 are known, I can use the recurrence relationship to find the relationship for P3 and Q3 and so on. So once P1, Q1 are known, using this equation, I can rapidly go on increasing the I up until n and find out Pn and Qn. In the end, if I look at this particular equation, so let me rewrite. We have Ti is equal to Pi Ti plus 1 plus Qi. If we focus on the equation for Pi and set I equal to capital N, so then Pn would become equal to Bn by Ai minus by An minus Cn Pn minus 1. But because Bn is equal to 0, we have Pn is equal to 0, and thus Tn is simply equal to Qn. And once Tn is known, I can simply put I equal to n minus 1, then I will obtain a relationship which will look like Tn minus 1 is equal to Pn minus 1 Tn plus Qn minus 1, where we'll recall that all the P's and Q's are already found out from the forward substitution step, and now my task is to just go backwards in T and evaluate all the values of Tn. So this is how the algorithm works. So let us go to MATLAB and see how we can implement it, and during this implementation I hope you will pick up a few commands of MATLAB. Let's see. So let me first define the number of points. And let us say the array is a very simple array. Let us say that the array is 2 minus 1 0 0 0 0 minus 1 2 minus 1 0 0 0 0 and so on, essentially implying that AI will always be 2, BI will be 1 and CI will be 1. Okay, so in reality, while doing the problem, you will of course construct the matrix on your own, but for this particular example, I'll just define these entries. Okay, in this case, let us try to define these entries randomly rather than having to do this. Okay, so I will define, okay, A1, rather let me write A equal to rand n comma 1, B equal to rand n comma 1, and C equal to rand n comma 1. So these three commands are So we just randomly initialize the 3 arrays. In reality, there may be 2s and 1s and all these things, but for this particular example, we'll just quickly do this. Okay. See, because this is a synthetic example, let's not focus on a particular problem. We also need D as random n comma 1. So A, B, C and D are all random arrays. Okay. So clear all will clear all the variables. N equal to 10 defines all the number of rows. So in accordance to the problem we just saw, we will define C1 as 0 and Bn as 0. So we will define C1 is equal to 0 and B end is equal to 0. So B end is so end is a keyword which signifies the last element of an array. So for I equal to 1 to n, so this defines the loop. Before that, we know that we will have n values of p and n values of q as well. So we will define p equal to zeros, n comma 1, q will also be zeros, n comma 1. It is always good to pre-allocate arrays. So if I equal to 1, we have this particular relationship. So P1, so Pi is equal to Bi divided by Ai, and we have Qi is equal to Di divided by Ai, and rather else. And so if I equal to 1, so if I double equal to 1 implies it is checking whether I is equal to 1. So if this particular statement is true, it means I is equal to 1, then P1 will be B1 by A1 and Q1 will be D1 by A1, like we have seen over here. And then we will simply write, if this is not the case, if I is not equal to 1, then the recurrence relationship is in terms of Pi, Bi and all these things. So let us define that relationship. Pi is equal to Bi divided by Ai minus Ci times Pi minus 1. Similarly, Qi will be equal to Di plus Ci multiplied by Qi minus 1 divided by this particular denominator, which I'll just copy and paste over here. Very good. So then we have defined the P's and Q's. So this particular for loop is essentially my forward substitution step. After this step, I have, sorry, this is not the forward substitution, this is the forward elimination. Then I will have the back. Let us now write down the backward substitution. Because it's a backward substitution, we must loop from n to 1. So for I equal to n minus 1, 1. So this is a short form of writing that I has to go from n to 1 in steps of minus 1. So we recall that if I is equal to n, then Ti is equal to Qi, else Ti is equal to Pi times Ti plus 1 plus Qi, and then we'll close the if else logical loop. So now if we run this, let us see what the values of t are. So t appears to be something like this, and of course because we've randomly initialized, let us see what a, b, so note that bn is 0, c, note that c1 is 0, and all these things are, so p and q are just found out. So alternately we may also use the inbuilt solver of MATLAB to do like a brute force solution. We may alternately do a brute force solution in which we will define the matrix and the d vector explicitly and then solve ax equal to b, because quite naturally this equation can also be written as ax equal to b, and which implies x equal to a inverse times b. So this is like a compact way of writing. So let us define how we will. So because we have defined a, b, c and d over here, we can obviously define this system, and because it's a tridiagonal system, we can use the inbuilt command diag to form the matrix capital A. So A is equal to diag of small a plus diag of minus b comma 1, implying at an offset of 1 from the central diagonal, I will input all the elements as minus of b plus diag of minus c comma minus 1, which is to say from the central diagonal I will offset by minus 1 and then write. So if I add these three diagonals, I should end up with the matrix A. And because D is already defined in the form of rand n comma 1, I can then simply write down the solution T using MATLAB. If I write it as Tm is equal to inverse of A multiplied by D. So let's see what we obtain. There seems to be some error. So this has something to do with the fact that the sizes are not equal, but depending on the version that you're using. So B, we cannot choose all the elements, so we have to choose 1 to n minus 1. So you will recall that if we look at the diagonal, it will include b1, b2, b3 and so on till bn minus 1, especially given the fact that bn is 0. Given the fact that bn is 0. Hence we must choose only the first n minus 1 elements of B. Similarly, we must skip the first element of C because C1 is equal to 0. So we write it as 2 to n. We extract a slice of C from 2 to its end element. We disregard the first value. Okay. So if we run this program, there we have it. So let's see whether T and Tm agree. So you will notice T and Tm are in excellent agreement. So the larger the matrix becomes, the more difficult finding this inverse of A becomes. See, essentially what I have done is I have defined the full matrix. If you print out A like so, you will see it's a tridiagonal matrix. Central diagonal, there is a shifted diagonal and all. So let me try to time this. So tick and tock are two functions. So I don't need to reprint, because once you call talk, it automatically prints the time taken. So between tick and talk, so this particular step took 0.001395 seconds. Let me also write tick and talk here. So the first tick tock would give me the time taken for forward elimination and back substitution. So when the matrix size is small, we see that the TDMA algorithm is rather slow, but I'm sure that as number of elements increases, we'll see that the TDMA is now significantly outperforming the matrix inversion procedure. As a matter of fact, for n 1000, it is really fast, almost 400 times faster. So I hope with the help of this program, see, every time I'm running this it's reinitializing with random entries for A, B, C, and already the TDMA has been solved. So now we are waiting for the matrix inversion procedure to yield its result. But because the matrix A is sparse, this particular matrix is sparse, and finding an inverse of a sparse matrix is not so easy. Okay, well, we have not done any optimization and all that, but the fact is still we haven't found out the solution using the matrix inversion method. We're still waiting. So in this example, we have seen how to initialize vectors, set them to zeros, set random vectors, and I hope you will refer to the help file in case you have a doubt regarding this. We saw how we could do the forward elimination. We saw how we could set conditionals that if I is 1, then you have to do this special case. Otherwise, you do the recurrence relationship that we derived earlier. Once we have the P's and Q's, you do a backward substitution. We saw how to do a backward loop, that is for I equal to n colon minus 1 comma 1, which is to say I goes from n to 1 in steps of minus 1. So finally we have the solution, and it took almost 93.5 seconds compared to approximately 4 milliseconds for the TDMS. So significantly outperformed. I mean, there are other algorithms which are comparable to TDMA, but TDMA offers a very easy way of addressing the problems for tridiagonal systems in which we have a simple program, and we can encapsulate this program in the form of a function. It will not make, so it will only make life easy for us. So anyway, as I was saying, once we have the P's and Q's, we can do a backward substitution over here, and we used advanced functions of MATLAB to form the matrix A and then find the solution using the inverse of A using this. So thank you for watching.